Mercier from UC San Diego. Patrick Mercier is an associate professor of electrical and computer engineering and co-founder and co-director of the Center for Wearable Sensors at UC San Diego. He received his Bachelor of Science degree from the University of Alberta, Canada in 2006 and the Master of Science and PhD degrees from MIT in 2008 and 2012 respectively. Professor Mercier has received numerous awards, including the NSF Career Award in 2018, the Biocom Catalyst Award in 2017, the UCSD Academic Senate Distinguished Teaching Award in 2016, the DARPA Young Faculty Award in 2015, the Bigman Young Investigator Award in 2015, the Hellman Fellowship Award in 2014, the International Solid-State Circuits Conference Jack Kilby Award in 2010, amongst others. He has published over 110 peer-reviewed papers in venues such as Nature Biotechnology, Nature Communications, ISSCC, 13 papers in the last 6 years, Advanced Science, and others. He is an associate editor of the IEEE Transaction on Biomedical Circuits and Systems and the IEEE Solid-State Circuits Letters. He is a member of the ISSCC, CICC, and VLSI, technical program committees, and has co-edited 2 books, Power Management Integrated Circuits and Ultra-Low Power Short Range Radios. His research interests include the design of energy-efficient mixed-signal systems, RF circuits, power converters, and sensor interfaces for wearable, medical, and mobile applications. The title of his talk is Power Management for the Internet of Things, so please join me in welcoming Professor Patrick Mercier.
All right, can everyone hear me okay? All right, thank you, Dina, for the nice and very elaborate introduction. So today I'm happy to be here to talk about power management for the Internet of Things. What we're going to find is that IoT applications have slightly different requirements than a lot of kind of more conventional system designs. And so we need to adjust the way we think and implement power management systems in order to accommodate these next generation needs. So before getting into the technical details, let's start with a little bit of motivation. So we can see let's get our slides working here. Here we go. Okay, so this is some data that's projected by Cisco. This was a couple of years ago, and you can see there's this enormous growth expected in IoT. And what we mean by IoT is essentially just connected devices everywhere. Okay, so I don't get that excited by having my toaster connected to the internet. Although, presumably you can eventually, if not today, start to buy connected toasters. But when we start to connect more interesting things like in smart home applications where you can connect your HVAC systems and do intelligent heating and cooling throughout the day while you're at home, while you're not at home, and so on, all the way to connected doorbells and so on. We're starting to see this explosion of growth in all sorts of areas, and areas, quite frankly, today we can't anticipate. Now, a lot of these devices currently rely on wall power. You think of your smart thermostat, you can wire that up into the power supply of your home, and there we don't have to care too much about energy efficiency. But there are many emerging applications, for example, in home security monitoring, industrial IoT, wearable sensors, etc., where you don't have access to wall power. And therefore, you need to power these devices from batteries or energy harvesters or alternative energy sources. So to that end, we really do care about energy efficiency. In addition, we also very much care about size for a lot of these applications, especially wearable type of devices, even some smart home devices. I recently went through an exercise of purchasing a home security system, and they delivered to me a bunch of small battery-powered devices, and they said the battery life will be about a year for each of these different window sensors and so on, which is okay. I'd like it to be 10 years if possible, right? And I'd like these devices to be even smaller and less obtrusive in the aesthetics of my home, for example. Okay, so there's a lot of interesting new requirements that are enabled when we start to think about these sort of IoT applications. So in terms of power management, there are several common constraints amongst many of these types of devices. So as I mentioned, most of them are going to draw their power from batteries. All right. Typically, this is going to be through a lithium-ion battery. And the reason we use lithium-ion is because they tend to have best-in-class energy density and therefore offer the longest lifetime possible. As I mentioned earlier, devices need to be small, and as a result, we can't use huge lithium-ion batteries, we have to use small ones. And so we really need to be careful about how we architect the rest of the system in order to make sure that we can have as long of battery life as possible. Now, energy harvesting is another approach, another opportunity that we can take advantage of in IoT devices, in the sense that many of these applications do have access to ambient energy. If we can tap into these ambient energy sources, it will allow us to extend the operational lifetime of these devices. However, these energy harvesters need to be small. Energy harvesting is, by its very nature, usually very stochastic, so we have to be aware of this when we're architecting our power management system. Now, these are common constraints, perhaps at least the first two constraints, with other very popular application spaces, for example, in mobile devices. So mobile devices is a very well-established market. We have billions of units and so on, and rich opportunities to do very well in this space. And like in the IoT, mobile devices are almost exclusively powered by lithium-ion batteries. And we'll get into some of the specific challenges of what it means to use a lithium-ion battery in a mobile or an IoT device. And mobile devices are also, size constrained. We can't have this enormous battery. We can't occupy a huge amount of area through our power management circuits, although if you do look at modern devices here, a lot of them are indeed have a huge amount of board area dedicated to power management. Okay, so if you look at this is a little bit of an older example here, the iPhone 5S. You have this power management SoC here. For the main devices, we have an RF power management SoC, and basically all around these two SoCs are a whole bunch of passives that are used to convert power. So not just from from an area perspective, power management is a huge occupier of area in modern mobile devices. In addition, they're also a large volume occupier in the sense that the inductors and in some cases the power management integrated circuits or PMICs are actually quite thick. And at least for this generation of phone, the iPhone 5S, the thickness of just the inductor, never mind the PCB, the battery, and so on, is about 50% of the thickness of the entire phone. Okay, so that's volume that can't be occupied by more battery and therefore is going to adversely affect your battery life. Okay, so this was a little bit of an older example. If you look at the latest example, in fact the phone that's in my pocket right now, the iPhone XS Max, you can still see that we have these power management integrated circuits and they're still surrounded by a whole bunch of passives, okay? And they're occupying a very large fraction of board area in these modern mobile devices, okay? So as we kind of progress forward in time, we're seeing this difficult trend. We want our devices to get smaller so we can put more batteries or just physically make them smaller. Certainly for IoT devices, that's very important. But at the same time, consumers expect more performance, and that endeavor requires more functionality, more complexity in your circuits, and therefore power demands typically increase. So we have these kind of competing trade-offs, okay? So how do we as power management designers deal with this? Well, unfortunately, it's difficult if we use kind of conventional approaches, all right? And the reason is, in conventional approaches, you have a very clear trade-off between efficiency and power density. Okay, so if you want to build a device that lasts a really long time, you can do that. You can build a very efficient power converter, but to do so, you typically need to use a large PMIC, large inductors and capacitors to process a lot of this energy. So it's very efficient, but we're operating at low power density because we have to occupy a large volume with all these passives. Okay. On the other hand, we could just choose smaller passives, run the devices harder, but if we do so, we're going to encounter more losses, so we get kind of over here. All right, so most designers kind of aim for a reasonable balance between these two trade-offs, where we want to make sure that we have reasonable efficiency and reasonable power density. Now, for a given topology, for a given IC technology and given passives, this trade-off is essentially a fixed curve. Okay, so how can we do better? We'd like to get somewhere in the top right of this curve here. Very high efficiency and very high power density. Now, the way that we've essentially been doing it in the literature and in industry as well is, well, there's not too much you can do, okay? So you have to try new things. You have to try new topologies. These can offer some advantages. Better packaging is actually a very powerful tool that power management designers really have to exploit in order to improve this Pareto optimal curve. Now, when I first started in IC design, I thought packaging was completely boring, and I didn't want to work on it ever, okay? I've since realized that packaging is so important in high-performance systems, especially in power management systems, that it is a part that you cannot neglect at all when you're designing your systems, and packaging has to be considered from day one. Okay, so that's the general landscape. How do we get into implementation examples? Well, let's first study the specifications that we're going to need to meet. So as I mentioned, typically we're going to operate from lithium-ion batteries. The big challenge here is lithium-ion batteries have higher voltages than what usual CMOS circuits want. Okay, so lithium-ion batteries are running from 3 to 4 volts, something like this. The voltage is variable during its discharge curve. You start at 4.2 volts. You spend the majority of the time at around 4 volts, maybe 3.8 volts, something like this. And then once you've discharged nearly completely, the voltage falls off a cliff. So that is in stark contrast to your CMOS circuits, which demand loads from, say, 0.5 to 1.8 volts, something like this. Most modern SoCs are requiring something like 0.8 to 1 volt, something like this. And most modern SoCs want that voltage to be variable. We want to be able to do dynamic voltage scaling in order to save power during dynamic workload events. And so we can't just supply fixed voltages anymore. That's just not sufficient anymore. Often, in most modern devices as well, we require different power domains. So we have, maybe many domains within the digital circuit. We have a domain for the analog circuits, for the RF circuits, and so on and so forth. So we need to be able to support this with our converters. Okay. So in general, for IoT and to essentially the same extent for mobile, is we want DC-DC converters that can cover the entire lithium-ion range, so we can maximize the energy utilization of the battery, with variable conversion ratios. And those conversion ratios range from about 1.5x to 10x. Okay? And it's that 10x number that becomes a very challenging number. Okay, so on average, for a typical kind of IoT device, we're going to have multiple modules within our SoC, or perhaps within separate chips. We're going to have modules that are doing sensing of the environment, for example, processing of this data, and transmission of the data or reception of commands to alter sensing parameters, and so on and so forth. So our power management unit needs to connect to a battery and process the energy demands of these 3 disparate loads. Now, typically, the power of these loads is not constant at all. Okay, so we have, most of the time, in many IoT devices, our data rate, our sensing demands are not continuous. Okay, that's not true for all applications. For example, video, we might have a very stable, continuous demand, but for a lot of environmental sensing, wearables, etc., most of the time we're sitting in an idle mode. We're not sampling at megahertz sampling rates, we're sampling at 100 hertz or something like this. For temperature, 1 hertz, 0.1 hertz is a perfectly reasonable sensing rate, okay? So most of the time the circuit is sitting in this low power sleep state where the sensors, the processor, and the RF modules are cut off or in some sort of low power sleep state, okay? Then we're going to wake up. There's some watchdog timer that's running in the background telling the node when to wake up, or perhaps it's a wake-up radio or something like this. Then we'll turn on our sensing unit, start to sense the environment, temperature. If it's a wearable device, maybe it's motion or some sort of electrophysiology, something like this. We're going to want to process this data or at least do something with it in the digital domain and then send it out. Okay. Now, this imposes a very strict amount of functionality on our power management. So we need to efficiently operate at super low voltages to make sure that we can run these watchdog timers and so on efficiently. We don't want to not be efficient at these low power levels because the circuit spends such a large amount of time there. Even though we're not consuming a lot of power, the overall energy draw from these low power sleep states can be significant. In fact, it can dominate the overall power consumption of your circuit if you're not careful. So we need to efficiently power loads at this kind of, let's say, 1 to 10 microwatt sleep state level, perhaps even lower in some applications. And at the same time, we need to be able to turn on our radios, which might consume tens of milliwatts depending on the transmission distance, and we still want to be efficient there. Okay, so we have a very high, many order of magnitude dynamic range requirement in our power converter. And this is what's a little bit different about if you compare it to many mobile devices, certainly if you compare it to kind of computer, laptop, desktop grade kind of power supplies, they have a much narrower dynamic range of operation, okay? So this means that we're going to have to operate our DC-DC converters in slightly different ways in order to improve efficiency over these very wide dynamic ranges. Okay, so other requirements, we generally want to regulate the output voltage. The load demands a very specific voltage, say 0.75 volts, and we don't want to stray too far away from that, even if you get large spikes in load current and so on and so forth. In particular, for analog and RF loads, we want that to be very stable and very low noise. And by noise, we mean very low amounts of ripple and so on, because if you do have this, then this can couple directly into your circuits and corrupt your signals. So you really want to make sure you have a very clean supply for your analog and RF circuits. Another general thought is, unfortunately, the larger the conversion ratio of our converter, the more difficult it is to achieve high efficiency and power density. And digital loads tend to like to work at low voltages, especially if you're concerned with energy efficient operation. And if you're operating at the top end of the lithium-ion battery, 4.2 volts, and you need to convert down to 0.5 volts, that's a large conversion ratio. We need to make sure that we can design our circuit to be efficient there, as well as, of course, at the lower conversion ratios when the lithium-ion battery has discharge and when we need higher performance operation through our digital or RF circuits or something like this. Okay, so we typically do this with switch mode power converters, and we'll get into the details of how to implement these. In theory, we can get very high efficiencies with these devices. In practice, of course, you never get 100% efficiency, you get something a little lower, and depending on how you choose your passives and your architecture and so on, you might get anywhere from 70 to 95, say, % or something like this. Okay. So this is the outline I'm going to propose for the presentation. We'll start with a very brief discussion on linear regulators. We'll get into some switch inductor converters, multi-input, multi-output converters using a single inductor to save area in these IoT applications. We'll briefly touch a little bit on switch capacitor circuits and then get into some discussions on hybrid converters that use both capacitors and inductors. Okay, so the first thing we can start with DC-DC converters is a linear regulator. Okay, so the easiest way to build a DC-DC converter is just build a voltage divider. Okay, if you take two resistors, you're going to drop the voltage, according to the resistive divider equation, and you can, just use that resistive divider output node as your power supply. Simple. Okay, and that's effectively what a linear voltage regulator or low dropout regulator does. Okay, so your load can be modeled by an effective resistance, and all we're doing is modulating the top resistance, perhaps through an error amplifier, or if you come to the presentations on Monday, we'll talk about some digital low dropout regulators through some digital switching devices. It basically just changes the resistance of this pass resistor until V out, or in this case called VDD, is regulated to some reference voltage. Okay? So very simple. If you want to build a DC-DC converter and you want it to occupy the lowest amount of area possible, choose this. It's a great choice. Okay? However, this is a lossy resistive divider. If our load is demanding some voltage and it's resistive, and we're dropping all of the other part of the voltage from the battery across this other resistor, then that's direct I squared R resistive losses. Okay, so this is not an efficient way to do this. So if you ignore the quiescent power consumption of the error amplifier, you can compute the efficiency of this converter as basically just the ratio of the output voltage to the input voltage. So as an example, if you're operating a device, in this example, the input voltage is 2.5 volts, and your output voltage is, around 2 volts, this is a perfectly fine solution. There's no reason to build an inductive or switch capacitor converter to do such a low dropout regulator. Okay, it's perfectly fine to use a linear regulator for this. Now, if you want to go from 2.5 volts down to 1 volt or less, then this is a terrible choice if you're interested at all in energy efficiency. So 2.5 down to 1 volt gives you less than 50% efficiency. Okay, so this is something that you probably don't want to do if that's your main application. Now, with that being said, most of our devices are running from lithium-ion batteries. Most of our SoCs run at 1 volt or less. Does this mean we don't use linear regulators? Well, the answer is, of course we do, but what we do is we convert that lithium-ion voltage down to some closer to SoC voltage first, and then we run the linear regulator on chip to provide a nice stable supply, especially to our analog circuits, although we also do this a lot in digital as well. So that means that we still have to pay attention to our linear regulators. We have to know how they work as a power management designer. But as a lithium-ion to battery or to SoC converter, they're not a good choice. Okay, so how do we build them? Very simply, you take your output voltage, you actually pass it through, in this case, an explicit resistor divider, and you change the value of these resistors in order to change the voltage that goes into your error amplifier and compares it to Vref. So in other words, rather than changing Vref to regulate the output voltage, you change the resistive divider, and that allows you to drive a gate which modulates a pass transistor whose resistance is determined based on the gate voltage, and therefore the resistor drop across this pass transistor will be whatever it needs to be to regulate the output voltage to the appropriate reference voltage. Okay. You usually also have some sort of decoupling filter here in order to filter out high frequency noise. Okay. If the resistance of this, or rather if the quiescent power of these error amplifiers are 0, then the efficiency is V out over Vn. R on, of course, has to be non-zero for this actually to work, so that's an error. Now, when we think of linear regulators, the first thing that should come to mind is what we call a low dropout regulator, or an LDO. Now, LDO itself is a special class of linear regulator, but we kind of use the terminology interchangeably. But LDO is basically a linear regulator that's specifically optimized to operate with a low dropout voltage. And that means we have a low voltage drop across this pass transistor getting from the input to the output. So again, if you happen to have a good DC-DC converter in front of your LDO, you can use your LDO to very finely and with very good precision and low noise regulate the output voltage with little efficiency loss, given that the loss is proportional effectively to the dropout voltage. Okay, so we build low dropout regulators typically by using a PMOS, a pass transistor. We could use an NMOS pass transistor as well, but in order to have a low dropout voltage, we typically need some sort of voltage booster in the feedback path. Otherwise, you have this VGS minus VT drop across the gate to source terminal of your pass transistor that you need to deal with. Okay, so that's really all I'm going to say about linear regulators. Again, if you want to make the smallest possible power converter, this is your choice. Okay, there's no real passives other than the decoupling capacitor. It turns out that there's some interesting ways to exploit this decoupling capacitor in a more intelligent manner and have it help or act within the regulator itself in order to get better area utilization of that capacitor. And that's perhaps a topic that would be good to discuss in the power session tomorrow. As I mentioned, great efficiency if your dropout voltage is low, but as your dropout voltage gets large, this is not the right choice to use. So the next logical question is, how do we do better? How do we get from lithium-ion to SOC voltages in one step and do this extremely efficiently? And the way to do this, of course, is to use switching converters, or converters that use passives alongside some switching elements. So as we mentioned, the linear regulator is nothing more than a feedback circuit that is used to modulate the resistance of a pass transistor. In contrast, a switching regulator does something entirely different. Okay, so what it does is we take our input voltage, or battery voltage, and we put a switch in series with it and the output, And this switch can connect either to the battery voltage or to ground. Okay, and if we switch this periodically, this node at the output, we'll call it VDD of T here, is going to switch between the input voltage, which is the battery, and ground. Okay, and it's switching with the square wave here. Now, if you can somehow extract the average value of this waveform, then you'll see that the average value of VDD of T is equal to the duty ratio, or capital D, times Vin. Okay, so if we just change the duty ratio of this waveform here, we can change the average value of the output. Okay, so this is really the basics of how a switching converter works. There's many other ways to understand how they work, but this is at the fundamental level what you're doing. You're chopping the input to create a square wave, and then you're filtering to take the average. That's all you're doing. Okay. Now, in the classic buck converter example, we build the filter with an inductor and an output capacitor. This turns out to be a good choice for a filter design. You don't actually need to do this. You could use a resistor and a capacitor, but that's not going to be as efficient. The resistor is a direct lossy element, whereas the inductor stores energy as it's processing the chopped waveform. Okay, so another way to think about this is that we're taking this linear regulator approach, which uses a resistor to create this voltage divider, and we're replacing the resistor with something lossless, an inductor, or perhaps even a capacitor in a switch capacitor circuit. So instead of dropping the dropout voltage as heat loss, we're dropping it as stored energy that is presumably later then delivered to the load, so that ideally we can have 100% efficient conversion. Okay, so that's two different ways to look at essentially the same problem. All right, so now, as it turns out, analyzing DC-DC converters is challenging to do it very accurately across all operating regimes because they are nonlinear and often time varying. Okay, so all of our linear time invariant system analysis that we've learned, throw it out the window. It doesn't apply here. Okay, now that's not to scare everybody off, because it turns out that if you can make certain assumptions and average over switching cycles and stuff, the average performance of the converter is readily understood and in fact readily modeled. Okay, so to do this, we typically invoke what's called periodic steady state analysis. And effectively what we're trying to do is take the average of various parameters in the circuit across a switching cycle in order to analyze how the device works. Okay, so for example, an inductor, under periodic steady state conditions, the average inductor voltage has to be equal to 0. Okay, and the reason, the intuition behind that is if the average voltage across the inductor is not 0, then that means you are going to be increasing or decreasing the current every cycle. And if that's true every cycle, eventually the current will go up to infinity or negative infinity and your circuit will blow up. Okay, so obviously that's not desirable. That's not what we want to do. We're not in the business of blowing up circuits. At least most of us shouldn't be. And so periodic steady state analysis says the average inductor voltage ought to be 0 across the switching cycle. Likewise, the average current going into a capacitor also has to be 0 across the switching cycle for the exact same reason. You can't keep dumping current into a capacitor and not expect its voltage to exponentially rise to unsustainable levels. Now, if this is true, then what we can do is in periodic steady state analysis, we can invoke average Kirchhoff voltage law rule, which basically says that the sum of voltages across all devices in a loop must be equal to 0 under periodic steady state, and likewise for currents. So we can use these tools in order to help us very easily and quickly understand how DC-DC converters work. Okay, so let's take a quick example, and we're going to get a lot more complicated quickly, so those of you who are familiar with power management, hold on. So in this simple buck example, we're going to assume that this output capacitor is very big, so that the average value of V2 at the output is just a constant. It's a DC voltage. Okay. So if that's the case, we're going to analyze this switching waveform, f of t. F of t is going to switch from value 1 to 0. When it's 1, you're connecting this node to the output. When it's 0, you're connecting the inductor terminal to ground. Okay. So you're switching the inductor voltage here, or this node Vx here, between Vin and ground. So we can go ahead and construct a loop around here. So Vx minus VL is equal to V2, or the output voltage here. And that's basically just says the sum of the voltage drops across this loop must be equal to 0. So the average value of Vx is just the duty ratio D times Vn. That's just taking the average value of this rectangular wave here. The average voltage across the inductor has to be equal to 0. And the average voltage of V2, we just said was, well, it's equal to the DC value of V2. So if you just solve this equation, it says V2 is equal to D times Vn, which is exactly what we expected from that prior switching analysis. And similarly, you could do this for the current, and the current in I1 coming from the battery is going to be D times the current through I2. Okay, so a very simple way to analyze a simple buck converter. Now in practice, we implement this buck converter with a series of switches or diodes. I'm going to show the simpler implementation here. We're assuming some ideal diode VD and some transistor activated by switch phi1. So in this case, we're going to turn phi1 on for a duty ratio D as a proportion of the switching period. That's going to connect the inductor voltage, the positive terminal of the inductor voltage directly to the battery. And the output of the inductor is equal to V2. So if V2 is less than the battery voltage, which is a normal constraint that we have in buck converters, then that means that the inductor current is going to ramp up during this phi1 phase. After the phi1 phase, we turn phi1 off, which means that this transistor is off. Now, the current in the inductor can't change instantaneously, just like the voltage on a capacitor can't change instantaneously. And so this current needs somewhere to go. So it was kind of circulating in this manner here. So as soon as we turn switch phi1 off, the current has to flow somewhere. What happens is this diode here turns on to keep this current going through the circuit. Now in this scenario here, the inductor voltage, it was positive in the first cycle. It was at V1 minus V2. When this diode turns on, if we assume it's an ideal diode, its voltage drop is 0. And then, therefore, we have negative V2 appearing across the terminals and the indicated polarity of this inductor here. And so, therefore, the current in the inductor has to ramp down. Now, according to our periodic steady state analysis, the average inductor current, or this delta I in the increase must equal to delta I in the decreasing phase, which according to, if you substitute in the equations shown up here, you'll get that the output voltage is again related to the duty ratio of the input voltage. Okay, so we've just derived this a few different times in progressively more practical implementations. Okay, so what I showed earlier was analysis for what we call the continuous conduction mode. And what we mean by that is the inductor current, when it ends let's say the phi1 bar phase, it immediately ramps back up in the normal phi1 phase. The current never actually reaches 0. There's always current flowing through this inductor. Now that is in contrast to the discontinuous conduction mode, where effectively what we do is we ramp the inductor current up, we ramp it down until it hits 0, and then when it hits 0, the circuit gets shut off and we wait for the next switching event. Okay, so let's just analyze this momentarily. When phi1 is on, we have the same ramp up. We have voltage V1 across the diode. When phi1 is disconnected, the current through the inductor has to go somewhere, so it's going to go through this diode, VD here, which means the inductor current is going to drop to negative V2. And then once the current hits 0, there's no other current path to go here. The diode turns off, the inductor current is 0, so it's happy to just stay at 0, and the inductor voltage becomes 0. Okay, the diode voltage becomes V2, because at DC, the inductor basically just looks like a short circuit. There's no current flowing through the inductor, so therefore this terminal of the inductor is also V2. So we can stay here for as long as we like until we activate the next switching cycle. Okay. Now we call this the discontinuous conduction mode because, well, as the name implies, we have a discontinuity in the conduction through the inductor. Now, you can go ahead and do the volt-second balance or the steady state equations, and it turns out the equation is a little bit more complicated than it was in the continuous conduction mode equation. The input to output voltage depends on the duty ratio, but now it also depends on the inductor, the amount of output current, and the switching period, and the input voltage. Okay, so you just have to be a little bit more careful. Now, why do we make this distinction in operation? Continuous conduction mode is what you're typically used to seeing in high-power converters. If you look into the power converter for this laptop, actually a lot of mobile phones use continuous conduction mode. And the reason this is popular for high power is because the inductor is always processing current. Okay? Even if it's ramping down, ramping up, etc., it's always processing current, and therefore it's always participating in any energy conversion, and therefore we're exploiting the inductor to its maximum opportunity. Okay? In this case, as we mentioned here, the output regulation is controlled exclusively via the duty ratio applied to, in this case, transistor phi 1. So if we want to regulate the output voltage, we just modulate the duty ratio, no problem. We do this through a pulse width modulation approach. Now, in continuous conduction mode, sorry, just to complete the thought, in CCM, and sorry, this is a typo, that should be CCM, not DCM. In CCM, because we're doing pulse width modulation, there's a limit to how short or how long we can make these pulses. And there's all sorts of practical implications of this. But fundamentally, it's really hard to modulate this over a very wide dynamic range. Okay, so most CCM converters, when you look at them up in the literature or for commercial parts, you see that they have a dynamic range of somewhere between 10 and 100x. Below that, their efficiency starts to drop off rather considerably. Now, in discontinuous conduction mode, we can regulate through one of two mechanisms. We can still do PWM modulation, just change the width of this phi 1 pulse. That changes the effective duty ratio of the circuit. We can also do pulse frequency modulation, where we adjust essentially the dead time between these pulses, or the discontinuous state. We adjust the timing of it, okay? Now, through pulse frequency modulation, we can operate over arbitrarily low frequencies, which allows us to scale our output regulation range to extremely low voltage values without a large energy penalty. Effectively, the switching losses scale with the switching frequency. If you're modulating via the switching frequency, as you scale down in switching frequency, you're going to scale your switching losses down. Okay? So as a result, PFM or DCM-enabled circuits tend to have a much wider dynamic power range, something like 10,000, maybe up to 100,000 or something like this, and we'll present some of the results of this later. Now, the downside of operating in discontinuous conduction mode is that there's lots of time where the inductor is not being fully utilized. Okay, so therefore, the power density of a discontinuous conduction mode converter is almost always going to be much less than that of a continuous conduction mode design. And so if you really care about volume, you'll probably want to operate in CCM and just run it as hard as you can. If you care about efficiency, particularly at back-off, then you probably have to use DCM. And then some works kind of enable a way to kind of do both. The control is a little bit more complicated, but it's not impossible to do. Okay, so we'll talk a little bit about more so in DCM momentarily. But before doing that, let's get into some CMOS implementation strategies and challenges. Of course, we don't want to use a diode in our buck converter there because it's going to have a 0.5, 0.6 volt drop across it, which will result in a fairly significant efficiency penalty. So what we want to do instead is use effectively just a CMOS inverter in front of our inductors, and this is going to operate as our buck converter. Okay, so in phase phi 1, we turn on this PMOS transistor that fluxes up the current in this inductor, and then when phi 1 turns off, we want to turn on phi 2, this NMOS transistor, to facilitate this continuous current path through the inductor, and then turn phi 2 off at the right point in time. Okay, so if phi 1 sets the duty cycle, how do we make sure that we control phi 2 at the right instance of time? If you're doing continuous conduction mode control, this is easy. You just turn phi 2 off when phi 1 wants to turn back on through your PWM waveform. That's no problem. In DCM, it gets a little trickier, right? So you're letting the inductor current go to 0, and then you want to turn this transistor off right when that voltage hits 0, for reasons that will become clear momentarily. If it turns off too early, then we still have current in the inductor, and that current needs to be dissipated somewhere. If we turn it off too late, then basically we have reverse current coming from the load back through the inductor in the opposite direction for no good reason. So we want to make sure that we avoid that scenario. In addition, we want to be careful about how we're turning on and off these switches. We really don't like to turn off a switch when it has a large voltage across it. Okay, just because there's all sorts of bad effects that go on. We'd prefer to turn on the switch when it has 0 volt across it, and turn off the switch when it has 0 current going through that switch. Okay, this is what we call soft switching. We want to turn the switches on and off at instances where, when we do so, there's not an immediate power penalty to doing so. Now, there's a lot of literature and a lot of things that we could study and understand about soft switching. We're not going to cover it in today's lecture, except for I do want to briefly discuss 0 current switching, because it's really important in discontinuous conduction mode converters. So let's go ahead and take a look at that now. All right, so this is a model of our buck converter in CMOS. I'm drawing these green diodes here. These are parasitic diodes intrinsic to the devices as we implement them in CMOS, and they will become important when we learn about the operation of this device. Okay, so in phase phi 1, we're going to turn on this PMOS transistor, so phi 1 is 0. This is going to ramp up the inductor current to some peak value. As soon as phi 1 turns off, i.e. phi 1 goes high, phi 2 also goes high, which turns on this NMOS transistor and allows the flux of current through the inductor to continue going until this ramps down. Okay. Now let's imagine in this example, we know the timing of phi 2 precisely. Okay, so we turn off phi 2 the instant the current of the inductor goes to 0. Okay. In that case, the inductor voltage node Vx here, it starts at Vin when it's connected through this power transistor. It goes to 0 when it's connected through the NMOS power transistor. And exactly when the current hits 0, we turn off phi 2, and the Vx node instantly jumps to VDD. Okay, because there's no current flowing through the inductor, therefore the voltage at the output has to be equal to the voltage on the other side there. Okay, so that's when life is good. Now let's imagine the scenario in the next phase where we ramp up phi 1, we ramp up the inductor current, and we ramp down the inductor current, but we accidentally shut phi 2 off a little early. Oops. Okay, so what happens here? Well, we've shut this transistor off, but there's still current flowing through the inductor. The inductor current can't change instantaneously. It needs to go somewhere. So what happens is this parasitic diode on this NMOS transistor turns on, and that facilitates the continuous loop of current here. Now, this parasitic diode is not nearly as good of a conductor as an on transistor. Its voltage drop is, well, the diode voltage drop. Its resistance is going to be larger and so on. So we really don't want this to happen. So what happens at node Vx here is that because this node is tied to 0, we now have current flowing through this diode. Node Vx now turns to negative VD, where VD is the diode drop. Okay, so this is a bad scenario, and this will conduct until the inductor current actually finally hits 0, at which point it goes back up to VDD, as in the prior example. Okay, now let's imagine on the next switching cycle, we said, oh, we shut off that switch too early, let's keep it on a little longer. Okay, so again, we flux up the inductor current, we ramp it down, and this time, oops, we left the switch on too long. Okay, so what happens in this case? Well, we left the switch on too long, so this node here, Vx, is 0, and the inductor current has gone to 0. Now, the other side of the inductor is at VDD. So now, all of a sudden, the inductor voltage is at VDD. The inductor voltage is at VDD. It's at minus VDD, basically. Okay, so what that means is now this path is going to have to conduct. Okay, so we're going to kind of keep throwing current through this inductor. The inductor current is going to get negative. Okay. Now, finally, it's negative now. We turn off that transistor. Well, the current has to go somewhere. And so what happens is the current has to go through this upper diode here in order to continue its current path until the inductor current ramps back down to 0. Or in this case, ramps back up to 0, I suppose. Okay, so in this case, node Vx here is going to be Vin plus V diode. This is a very large voltage. This is a very undesirable situation. It introduces a ton of extra losses. Okay. All right, so we definitely want to avoid this scenario. Now, the most typical way to do this is to basically just put a little current sense resistor in series with the inductor, put a differential amplifier across this current sense resistor, and measure when that current hits 0, and when it does, turn off transistor phi 2. This is called zero current switching in a DCM converter. Doing so requires a continuous time comparator, and that may consume a significant amount of quiescent power, especially when we're operating at very low frequencies for very low power loads. Okay? So we want to perhaps try and avoid a way to do this. So I'm going to present two different ways to avoid the power penalty of doing this. The first way is rather than putting in a sense resistor, which has losses of its own, it also has quiescent power issues of having a continuous time comparator, we can build effectively a bang-bang control kind of technique. Okay? And so what we do is we basically look at the Vx node at the moment that phi 2 turns off. Okay? So if phi 2 turns off, and we look at Vx and we see that it's negative, then we recognize, oh, we turned off too early. Let's increment a counter, and on the next cycle, turn off a little bit later. Okay? So we can use this as one of our dimensions of our control. Now, on the other hand, if we take a look at the node Vx as soon as the transistor turns off and we've been on for too long, then all of a sudden that node is much larger than VDD. It's a very high voltage. Okay, oops, in that case, we've kept that transistor on too long. All right, so in that case, let's increment a counter, let's decrease the width of period phi 2. And we can use this kind of as a dual bound hysteretic or bang-bang kind of control loop in order to control this without requiring a continuous time comparator. All we need is a clocked comparator that is clocked on the falling edge of phi 2 in order to make this control loop happen. Now we can build clocked comparators much easier than we can build continuous time comparators. They take much less energy, and therefore this can be a very energy efficient way to do this control. So effectively we have our clock comparator here. We're comparing V drain, or Vx in the prior example, to ground on the falling edge of phi 2. If we're early or late, we'll assert some increment or decrement logic that's going to adjust the pulse width, in this case of phi 2, through a resistive RC delay line in this particular example. I pulled it from this reference paper here. So this is a very easy way to do it. Of course, we could still use our continuous time comparator, but that's going to have a fairly large power penalty. I'll discuss a little bit later in the presentation one way to mitigate that power penalty. Okay, so let's assuming we've built our control loop, but we're going to operate in discontinuous conduction mode for IoT applications. What are the major loss mechanisms of our converters? There's various loss mechanisms. The two big ones are conduction loss and switching loss. Okay, so conduction losses are nothing more than I²R losses. Okay, this happens in the switch when the switch is on. This happens in the inductor, which has a finite DCR or effective resistance. This is just direct loss, thermal loss from I²R. Okay, we also have switching losses, and this is caused by turning on and off the gate capacitance of your power transistors. It's caused by turning on and off the parasitics within the converter itself. Okay, now these two come at a trade-off. If you increase the size of your switches, you're going to decrease R on, and therefore your conduction losses set by I²R on are going to decrease. Great. But your switching losses are going to increase because now you have a larger gate, it has more capacitance, so CV² goes up. So a direct trade-off. Now, usually the optimization is set such that your switching losses roughly equals your conduction losses, and that's going to be the rough optimal point here, as indicated by this graph here. So as your switch size goes up, your switching losses increase, but your conduction losses decrease, and the optimal point is when they are equal. Okay, so this is a rough idea of how to do this optimization. Now, I have to say this optimization is for one value of current. All right, when you go down to a lower current, this optimal point is going to change because I squared is going to change. And so this is why it's rather difficult to operate over large dynamic ranges without using other circuit tricks in order to help. Okay. All right, so before getting into some of those other tricks, let's talk a little bit more about a few different of the topologies one can imagine using. So we talked about the buck converter in phase phi 1. We have current fluxing up the inductor over here. In phase phi 2, the diode discharges the current on the inductor. We can also build other types of converters, boost converters, for example, where we take our input voltage, we flux up current in the inductor in phase phi 1, and then on phi 2, we release that current to the load. Okay? Now this is used to convert a low input voltage to a high output voltage. This would be useful in IoT for energy harvesting devices, for harvesters that specifically provide low input voltages. Okay? So with the same periodic steady state analysis that we observed before, the voltage across the inductor must be equal on average across a switching cycle. We see in the first phase we have V1 appearing across the inductor, and in the second phase we have V1 minus V2 appearing across the inductor. So just by equating the area of these two squares here, we can derive the transfer function, which is equal to 1 over 1 minus the duty ratio, D. Okay, so if you have a duty ratio very close to 1, then you're going to get a very large step up because 1 over a small number becomes a very large number. Okay, so this will be useful for a lot of energy harvesting applications. Now, one thing I'd like to point out is that these two converters are what we call a direct converter because the source is directly connected to the load, at least through one part of the switching cycle. Okay? Obviously, if we have a direct converter, then presumably there is a other class of converter called an indirect converter. And indeed, it might look something like this. Okay, so this is what we call the inverting buck-boost converter. On phase phi 1 of the clock, we flux up the inductor through this transistor. And then on phase phi 2, the inductor discharges through the diode over here. So this is called an indirect converter because the input is never directly connected to the output. We flux up the inductor on one cycle, then we disconnect the source, and we let the inductor discharge on the other half of the cycle directly to the output. So again, we can do our volt-second balance or our periodic steady-state analysis here. On phase phi 1, the inductor voltage is V1. In phase phi 2, the inductor voltage is V2. So if we take the average of these two, we see that V2 over V1 has to be equal to minus D over 1 minus D. Okay? So you'll note here that this is a negative sign, and so this is why we call it an inverting converter. We take a positive voltage and we generate a negative voltage. As D varies from 0, when D is 0, our conversion ratio is negative infinity. When D is 1, our conversion ratio is 0. So we're converting between negative infinity and 0. So as a result, this is actually operating in both buck and boost modes. So we can increase the voltage if we ignore the negative sign, or decrease the voltage if we ignore the negative sign. Now, in CMOS, we typically don't like dealing with negative voltages. You can do it, but you have issues with the bulk and so on, and so we prefer not to. So in CMOS, if we want to build a buck-boost converter, or a converter that can operate in both the buck and the boost mode, this is the suggested initial topology. Okay? So effectively what we do is we take a buck converter, and we cascade it with the boost converter using the same inductor, and that creates our buck-boost converter. Okay? So this can work in the following manner. In phase phi 1, we have this PMOS transistor and that NMOS transistor on, and so we're fluxing up the inductor current in this manner here. And in phase phi 2, we turn on this NMOS and that PMOS transistor, and we deflux the inductor current to the load in that cycle. Okay? So again, in phase phi 1, we're applying V1 across the inductor, In phase phi 2, we're applying negative V2 across the inductor. So if you go through the math, you get the same equation as we got in the previous slide, except now it's not negative. It's d over 1 minus d. Okay? So this allows us to, as we change the duty ratio from 0 to 1, we get an output voltage that varies from 0 to infinity. Of course, we can never get actual 0 and we can never get actually infinity, but it's the theoretical result here. Now, why would we want to use a buck-boost converter? One possible reason is because we are operating, let's say, from a lithium-ion battery. And this battery is running from 4.2 volts all the way down to, let's say, 2.8 volts. And let's say in this application, we needed to generate 3.3 volt supply for one of our circuits. Well, you can't use a buck converter when your input voltage is 2.8 volts and you're trying to generate 3.3 volts, right? And so this is where something like a buck-boost would come in handy. This is also very handy for energy harvesting. Let's say your energy harvesting source varies from 1 volt to, let's say, 100 millivolts, and your load voltage requires 0.6 volts. Well, when your input is 1 volt, you need buck mode. When your input is 100 millivolts, you need boost mode. So this is where we would use this kind of converter. Now this is another one of these indirect converters because the input is never directly connected to the output. Now, we prefer not to use indirect converters if at all possible because we just effectively have more ways to lose energy compared to a direct converter. Okay. Now, we could, for example, take this converter and make it a direct converter. So, for example, we could take this converter and turn it into a buck converter. Okay. Basically, we just never turn this switch on, and we always keep this switch turned on. Okay. So this is just a short circuit. This is open, and then this looks exactly like a buck converter. Okay. Now, it's not going to be quite as efficient as a buck converter because we have extra I²R losses occurring across this transistor. We don't have any switching losses associated with this transistor, but there's I²R losses associated with this transistor. But we will get better performance than if we just operated in the buck-boost mode, because in the buck-boost mode, you're turning on and off this transistor, and you're turning on and off this transistor. You don't need to do that if you know that you can operate in the buck mode. This just gives you a little bit of flexibility to dynamically reconfigure which mode of operation you're working in depending on the application demands. The only time you would work in the buck-boost mode is if you want to regulate to a voltage close to 1, for example, because at close to 1, it's hard for the boost or the buck converter to work effectively. So this is where the buck-boost does its work the best. We can likewise reconfigure this buck-boost into a boost-only mode by permanently turning on this transistor and open circuiting this transistor, and then this just looks like a boost converter. Okay, so that was a fairly basic introduction into inductive switching converters. Now let's get a little bit more into more modern design techniques and talk about some of the challenges associated with energy harvesting and multi-output conversion. So as we alluded to earlier, most of these IoT kind of devices have these very wide dynamic power ranges that we need to support if we want the device to operate correctly. Now, the average power constraint of our application might be rather small, especially if we spend a lot of time in the low power sleep state. So if we have a battery on board, and the battery is typically used to supply the power for these kind of high quiescent or high instantaneous events from the radios, for example, then there's an opportunity to enable some energy harvesting to either directly power the system when it's in this low power state, or if it generates more power than we need, to actually go ahead and recharge that battery. Okay, so adding some energy harvesting, maybe not as the only mechanism to power your device, but as an auxiliary mechanism can help improve your battery life sometimes dramatically. And the reason I say most of these kind of systems aren't going to rely exclusively on energy harvesting is because, well, as I mentioned earlier, energy harvesting is stochastic. If we're going to use light, a photovoltaic cell, then we'll get a reasonable amount of energy in this room, for example, but we'll get a heck of a lot more if we put it outside in the sunshine, and of course we'll get zero when it's nighttime. Okay? Or if it's a wearable device and it happens to be under your shirt, you're not going to get a whole lot of power there, right? So you need to architect your system to be aware of the stochasticity and make sure that you're always going to have energy available, and that's typically through inclusion of a battery. Okay, but unfortunately, on average, it's often the case that the energy harvester doesn't provide enough power for your system to operate on average, okay? Which is why you need a battery. That battery may need to be replaced. But there is an opportunity for us to perhaps, let's say, include some other sources of energy harvesting. Ideally, some orthogonal sources of energy harvesting that might help increase the average power across a wider range of conditions. Okay? So most energy harvesting today in IoT is done through light, maybe through thermoelectric generation. Some people do RF, although that's a little bit difficult, especially at distance. One thing that my research group has been doing a lot recently is biofuel cell-based energy harvesting. So it turns out that we're doing a lot of work on building wearable devices that measure not only electrophysiology, but physiochemistry. So these are things like blood sugar levels, glucose, lactate levels, these are levels of exertion, and so on. And it turns out that glucose, lactate, and so on are excellent biofuels. Okay, so we went ahead and did this project where we built a biofuel cell-based energy harvester, where we take some enzymes, the enzymes catalyze a reaction with glucose or lactate, which produces electrical energy. So we have this neat demo where we fabricated these screen-printed biofuel cells. We put them on a wristband. We took the output of this energy harvester, which is on the order of a couple hundred millivolts, through a boost converter. And we took the output of the boost converter and attached it to a watch, which we then removed the batteries. Okay? So we did this interesting experiment. We put the device on, we put the watch on, and nothing happened. Okay? But then we started working out. As soon as we started sweating, there's lactate in sweat, the device turned on and was powered from human sweat. Okay? So this is an example of a biofuel cell-based energy harvesting system. In this particular example, we were able to get about 100 microwatts per square centimeter of power density. In a subsequent example, I don't have it in the slides here, but in a subsequent example, we were able to show about a milliwatt per square centimeter of power density, which is probably more power than we'd get in this room through a photovoltaic cell, but not quite as much as you get from a photovoltaic cell under direct sunlight. So it's a nice auxiliary source of energy harvesting. So one thought we have is, given that we have these interesting sources of energy harvesting, why don't we combine them into one platform? You know, it's unlikely that you're going to have light all the time. It's unlikely for a wearable device, for example, that you're going to be sweating all the time. It's unlikely that you're going to have a strong thermal gradient between you and the ambient environment all the time. But maybe, on average, one of these conditions will be true, and if so, that will increase the total amount of energy available to our system. So what we'd like to do is we'd like to build a power management unit that can harvest from multiple sources of energy simultaneously, process this energy, including the energy from a battery, and deliver it to multiple outputs. Okay, so we'd like multi-input, multi-output converter here. Now, ideally, we also want to build this with a small form factor, especially if this is a wearable or an IoT device that needs to go into the corner of a room or something like this. We want to make sure that these devices are extremely small. Okay? So in order to process this energy, we'd love to be able to do this with a single inductor. Okay, so we call this a multi-input, single inductor, multi-output converter, or SIMO. Okay? Now, the idea with this particular work is that we want to dynamically switch between different load conditions, between different energy harvesting conditions, in order to do maximum power point tracking and output regulation using this single inductive platform. So the platform works as follows. If we have plenty of energy from the harvesters, that'll be used to directly power the loads, as well as perhaps charge the battery. If our harvesting sources are not quite enough, then we'll use whatever power we have to deliver it to the loads, and any auxiliary power that the loads demand will come from the battery. And then if the harvester power is just very little, we're in a dark room, not sweating, and there's no thermal gradients, then we'll just power exclusively from the battery. All right, so how might we do this? Well, There's a vast body of literature on SIMO, or single inductor multi-output converters. There's been lots of great work on this application space. I encourage you to read the literature in this space. It's very fascinating. There's also been work on simultaneous energy harvesting and voltage regulation. In this early work, they were using a two-stage converter. So in other words, they harvested energy, stored it onto a storage cap, and then took that energy and regulated it to a load. And the reason for doing this in the first place is because it turns out it's a little difficult to simultaneously perform maximum power point tracking at the energy harvesting source and regulate the load all with a single inductor. We'll talk about how to do it momentarily, but at the time that was a difficult challenge. Then there's other folks who have proposed doing multi-input energy harvesting, again using a two-stage approach here to first store the energy and then use it to regulate a single output voltage. There's other work, including work by our educational session chairwoman, who proposed to do energy harvesting and then power multiple loads. And then that's just in contrast to this work where we tried to do multi-input and multi-output harvesting all with that single inductor. Okay, so there's many challenges here. Let's go through them one by one. The first challenge is we want to be able to extract the maximum possible power from all three of these sources simultaneously, again using that single inductor. We don't want to leave any energy on the table. Next, we want to be able to independently regulate all of the loads with a very large dynamic range to make sure that they have all the power that they need. We want to do this with a single inductor. Okay, so we're regulating two sides of the inductor across multiple loads and multiple sources. It turns out this is not so obvious, let's say, how to do this. And we want high end-to-end efficiency across a wide dynamic power range. We want this to be efficient at a microwatt during the sleep state, and we want it to be efficient at, say, 60 milliwatts when we're in our high power transmit mode, for example. So all of this needs to be controlled by a very low quiescent power controller, and we need to optimize the switches and so on to make sure that we can be efficient over this wide dynamic range. So let's start by looking at the maximum power point tracking. Now there's many ways to do maximum power point tracking for solar cells, for example. The approach we used here is called the fractional open circuit voltage approach. Basically what happens is that as the light level increases, the maximum power point in terms of the input voltage changes. Okay, so we can't necessarily just build, a input resistive divider kind of circuit, which we typically do for a lot of other sources of energy harvesting. We need some other way to do this. People use hill climbing algorithms and so on. So it turns out that if you just sample the open circuit voltage of the solar cell, it turns out the maximum power point of that solar cell is roughly 3/4 of that open circuit voltage. Now this is not perfect, but it's pretty good and it's much simpler than doing a hill climbing algorithm or something like this. The same situation is true in thermoelectric energy harvesting as well as biofuel cell based energy harvesting. So in this particular work, we decided to do this fractional open circuit voltage regulation. Okay, so all we have to do is, in order to perform MPPTs, we need to know what this open circuit voltage is, divide it by the fraction, and then regulate the input to that voltage. Okay, so in order to do maximum power point tracking, we just have to do input regulation. So it turns out that we can do this through a number of different ways. The perhaps easiest way to do it is by adjusting either the on time of the inductor current fluxing up or the switching frequency. So this is implemented as that CMOS Buck-Boost converter. On phi 1, we flux up the inductor on this in this phase, and then on phi 2, we let that inductor current release to the output. Now, under the discontinuous conduction mode in this Buck-Boost converter, you can effectively model the input resistance of the circuit, and you can kind of go through the math just by taking the average current and the average voltage across the switching cycle. And the resistor is proportional to the switching speed and the on time of that first phase there. So another way to think about the energy harvesting criteria is that once you've selected your open circuit voltage that you periodically sample and refresh, then it's just a matter of regulating the input V-harv voltage here simply by adjusting either T-switch or T-phi1 in order to get that input resistance set correctly. Okay. So in this work, what we decided to do is we adapt the switching frequency or the switching period to the available amount of harvested power in order to set kind of a coarse regulation, and then we do fine-tuning by switching the T-phi1 during regulation. So we do this very simply through a hysteretic comparator. Okay, so all we do is we compare the harvester voltage with the desired maximum power point voltage and say, are we above or below this? If we're above this, no need to switch that particular harvester. If we're below it, say, oh, we've fallen below our regulation bound, let's invoke a switching cycle in order to extract some energy from that harvester. Okay. Now this could be done with a low power continuous time comparator, so actually we don't need a clock. This can be done completely asynchronously, as long as you have a good zero current detector circuit, which I'll talk about momentarily. So we can do this through multiple of these sources. Okay, so on one switching cycle, we let's say the photovoltaic output voltage falls below its regulation threshold. So then we can go ahead and turn on the power stage to ramp up and then deliver that energy to the load. Now, once we've ramped up and extracted energy, we'll be good for a little while, so we can wait. This waiting period depends on the size of the input decoupling capacitors. Then we can do this, throughout the cycles as each energy source requires some maximum power point tracking. Okay, so just looking at this more carefully, we see that the comparator for the photovoltaic will turn on here, and then maybe it takes a few switching cycles until it needs to be power extraction again. And likewise for the BFC, the biofuel cell, and the TEG, or the thermoelectric generator. Now the important thing is we want to operate this over a wide dynamic power range, which means we're going to have to operate in the discontinuous conduction mode. Now when we do this, we typically want to, when we're idling, we want to enable these bottom two NMOS transistors to put the circuit in the freewheeling phase. This just minimizes voltage ringing on the inductor and just makes sure we're in a good low quiescent power state. Okay, so we'll stay in this freewheeling phase until the next energy harvester gets triggered by a hysteretic comparator, and then we'll continue on through this approach. Okay, so that's about, and just to be clear, we stop when the zero current detector determines that there's zero current switching through that inductor. And we'll talk about that circuit momentarily. Okay, so far we've talked about the inputs. What about the outputs? We've just labeled them as load here. Okay, well, there's multiple ways to do this. For each switching cycle, you can deliver power to one of the loads. No problem. Next switching cycle, next load, and so on. Or for each switching cycle, you could deliver power to each of the loads individually as each load requires power. Now, what we like about this particular approach on the right here is that for the same effective switching frequency at the input, we get a larger effective switching frequency as viewed by the outputs, and so this improves our ability to regulate and increase efficiency. Now I should point out that the transition times between these loads are completely determined by those hysteretic comparators. Now here's the big challenge. Let's say in one switching cycle, the photovoltaic needs energy. And in that switching cycle, the load 2, for example, also needs energy. Now T-phi1 is set by the MPPT condition. T-phi2, as we ramp down here, is set by the zero current detector. But what happens if load 2 doesn't require that much power? In fact, it's going to be very rare that it just so happens that the amount of energy demanded by the input harvester is exactly the same amount of energy demanded by the load. It's going to be rare that will happen perfectly. Okay, so this is actually a big trade-off that we saw in prior work. And so the way that we chose to compensate for this is to if we have, we're setting our MPPT by T-phi1, and if during delivering power to load 2, we've kind of completed the cycle and it doesn't need any more power, then we just take that energy and drop it back to the battery. Okay, so doing this decouples the input regulation used for MPPT and the output regulation, provided, of course, that we have the battery and the battery can support charge delivery. If the battery is completely full and the loads don't need anything, then basically we just won't invoke a harvesting cycle, and we'll let the harvester get away from the maximum power point because we're totally energy full. Okay, so there are some cycles where we're going to need to get power from the battery. So in this case, we turn on this switch, we flux up the inductor, and then we can deliver energy to one of these 3 different loads here. And we want to make sure that the on time of the battery is just enough in order to deliver just the right amount of energy to all of the independent loads. Okay? So what happens if we don't have that condition? What happens if we have a fixed T phi 1, we take a lot of energy from the battery, and the load just doesn't need it? If the load doesn't need it and we don't do anything about it, then we're just going to deliver more energy to the load, its ripple is going to increase, and we have all these extra conduction losses coming from this approach for no reason. Okay? So what we have to do here in order to improve this situation is do T phi 1 calibration. Okay, so in other words, based on how much current we see through the inductor and how much energy the loads need, we can adjust the T phi 1 time to make sure that the amount of energy delivered to L2 in this example is just the right amount. Now, if we delivered a little bit, if we extracted a little bit too much from the battery, then what we can do is actually just dump that back to the battery. Okay, now this is an inefficient process. We don't want to draw that energy from the battery, use some of it, and then dump the rest back. And this is precisely how we do this control. So we're basically running the control to make sure that the battery energy delivery is as small as possible in that last phase there. Okay. All right, so this is basically the approach. We can take energy from the energy harvesting sources, deliver it to the loads and the battery, and so on. And then in some cases, if we need energy from the battery, we can go ahead and use the energy from the battery. Now, all of this is done asynchronously. They're all done through these hysteretic comparators here from each of the input sources, each of the loads, as well as the energy from the zero current detector. Now, the zero current detector is specifically operating via the on resistance across the switch that we're using here. So we're not actually including an additional series resistor in series with the inductor in order to do this measurement. So these comparators on the left here, my computer just froze. There we go. So these comparators on the left, they trigger the controller for energy harvesting. The comparators on the right trigger the controller to deliver energy to the load, and the ZCD controls the end of the switching cycle. Yeah, the computer is very frozen. Okay, good. So it turns out that if you're not careful, so these comparators here, these don't need to operate with high timing precision. So they can be implemented as fairly low power continuous time comparators, 60 nanowatts for all 3 on the left, 90 nanowatts for all 3 on the right. The zero current detector, if you're not careful, it can consume quite a bit of power because you do need its bandwidth to be very fast to make sure that when that inductor current goes to 0, you immediately turn off those transistors. So we can reduce the power, the average power of the zero current detector circuit simply by duty cycling it as well. We know we don't need to detect zero current if we're already at zero current and we're in the freewheeling phase, or if we're in the inductor current ramping up phase. We know we're not trying to detect zero current there. So what we can do is we can install these effectively these power gating transistors here that turn off the continuous time comparator when we're not using it. Okay. Now, given that the average duty ratio of a low power IoT device is going to be rather low, this can have significant savings. So for example, at an average power consumption of 10 microwatts, this decreases the quiescent current of the zero current detector by about 3 orders of magnitude, from 2 microwatts to 1 nanowatt. There's a few other things that we have to pay attention to if we want to design this for very low quiescent powers. When we're in the freewheeling phase, these two switches are on. These power transistors here, they're off, but they're big transistors. They have a lot of leakage. Likewise with these transistors going to the load. These guys over here don't have as high current capabilities, and their voltages across them are a little lower, so we don't worry about these guys too much. So one way to reduce the leakage losses of these devices is to, come on computer, stack the two devices in series. And the reason this helps is because this PMOS transistor, when we turn it off, it has 1.8 volts at its gate and at its source. So this transistor is off in the nominal sense. But this transistor here has 1.8 volts on its, you guys can't see my pointer, can you? Yeah, I don't know what's going on with this computer. Okay, well, the bottom PMOS transistor in the power stage has 1.8 volts at its gate, and at its source it has 0.9 volts, and so that transistor is in super cutoff, and so therefore its leakage power is going to be quite a bit lower than the nominal case, despite these transistors being doubled in size. So this reduces leakage power by about 9x. The other thing that we can do is we can binary weight these power transistors and do switch size modulation. And what we mean by that is, if my slide would advance here, what we mean by that is when we're operating at low power levels, low current levels, we don't need super low R on because I squared R on is not a large number. And so we can reduce our switching losses by switching the smaller transistors rather than big ones. Okay, so we can do switch size modulation. In this particular example, we only had 2 bits of control for switch size, but this did allow efficiency improvements by upwards of about 24%. So this particular design was implemented in a 28 nanometer FDSOI process. The total area of the converter was about 0.5 square millimeter, and the area breakdown is on the slides there. So we went ahead and measured this. We showed that we could power all 3 output loads at different load voltages and different load currents. You can see the zero current detector switches really fast when the circuit initially turns on in order to quickly ramp up the voltages on the loads. And then once the voltages on the loads gets stabilized, then you can see the zero current detector starts to slow down a little bit and just regulates on demand. So this shows the asynchronous behavior of this type of circuit. Now, in a multi-output converter, an important test is always to make sure that if you have a big voltage step, for example, from 1 micro to 1 milli on one of the loads, that its load voltage is well regulated and the other load voltages don't droop and have some cross-regulation effects. And due to the asynchronous nature of this circuit, we could respond very quickly. And in this very fast voltage step on load 1, you can see that load 1 doesn't really droop. You can see that its regulation frequency increases substantially when it goes to a higher power level, as expected through the PFM control. And loads 2 and 3 don't really change at all. Their ripple voltages is about 30 millivolts or less. Likewise, we can do harvester. We can look at the harvester side. When the load 3 has a step on it, we see that the harvester voltages also continue to keep their regulation. We could do harvester load steps where we turn the light on, for example, in the PV cell, and we see that everything is still good in those examples. If we take a look at the efficiency, you can see here we have an efficiency above 80% at very high powers. This is at about a few tens of milliwatts. And with switch size modulation, when we go down to very low powers, all the way down to a microwatt, we can keep that efficiency level above 70%, even at 1 microwatt of power consumption. If we didn't do switch size modulation, this efficiency would fall down quite a bit, all the way to about 55% at 1 microwatt. So the switch size modulation is fairly effective. This is at a lower voltage. If we're at a slightly higher voltage, our efficiency is even better than 75% over multiple orders of magnitude of dynamic range, just as desired in IoT applications. We also show that if we do T-Phi1 battery on-time calibration across the output dynamic range, we can improve the efficiency quite a bit. The peak efficiency in this measurement was 89%, and at 1 microwatt of power, we're above 75% efficiency. If we didn't do this calibration, we would be 45% efficiency or something at this back-off number, which is very poor, and we'd obviously like to avoid. So this is has been an example of a multi-input, single inductor, multi-output energy harvesting platform optimized for use in IoT applications. Now, if you go ahead and compute the power density of this circuit, it's not going to be as high as a comparable continuous conduction mode converter. But because we're only using a single inductor and we're supporting all three loads and all three energy harvesting sources, with just this one little inductor, it does start to meet the needs of many of these IoT devices. And in fact, if you compare its power density compared to other work that operates over these very wide dynamic power ranges, and that don't support as many loads or sources as this one does, you'll see that this approach through the asynchronous control and so on actually does a fairly good job. Okay. I'm going to go ahead and skip through some of the slides on switch capacitor converters. I didn't have too many on here. I wanted to just introduce them and say one of the main challenges with switch capacitor circuits is that although they can be fully integrated on chip, they are only typically efficient at limited ratios of input to output voltage. And my group and many others have done a lot of work on implementing many ratio switch capacitor circuits that allows us to regulate over wider input dynamic ranges. There's still challenges on how to do this efficiently, how to do this across multiple sources, how to share resources, and so on. And so there's still a lot of research, I think, left to be done in the switch capacitor approach before it becomes a very viable alternative, at least commercially. So it's still very promising, I'm hopeful, but there's still a lot of work left to be done here. So what I wanted to conclude my presentation with is a brief discussion on hybrid converters. Okay, so switch capacitor converters technically have capacitors have higher energy and power density than inductors, but have these challenges. Okay, and so one of the nice things about hybrid converters is we kind of use the best of both worlds. We use the best of capacitors and inductors together. Okay. So typically what we do in modern SoC design is we build our power management IC in some old process that can support the high voltages needed by lithium-ion batteries, and then we step this down to a much lower voltage on-chip through an LDO. What we prefer to do is put this all on the chip. Now, whether or not the passes are on the chip or not, that's another discussion to have perhaps, but we'd at least like to have all of the transistors on the scaled CMOS process. So it turns out that this is hard. It's hard in a modern process because typically we only have low voltage transistors. In 28 nanometer, for example, we don't have a 4 or 5 volt transistor. They just don't exist in that process. So what that means is we have to stack transistors on top of each other. This can result in poor efficiency if you're not careful. There's all sorts of other challenges. I'll skip over these for the time being. And then there's all sorts of implementation strategies that other people have done. So the idea with a hybrid converter is rather than use a big bulky inductor, rather than trying to do things on chip with capacitors, which is difficult, let's try the best of both worlds. Let's use a little bit of inductance and a little bit of capacitance and try and build something that can exploit transistor stacking and can be efficient even when operating at high voltages. And so the basic idea is this. If you want to build a buck converter in a scaled CMOS process and have it operate from a lithium-ion battery voltage, you need to stack transistors in order to block these higher voltages. So for example, each transistor can block 1.5 volts. Stacking 3 of them, you can get to blocking 4 volts. So the challenge with this approach is that there's efficiency losses, you're going to need a fairly large inductor to be efficient, and so on. So the idea with a hybrid converter is, given that you have these stacked transistors, why don't you exploit it and add a few flying capacitors? If you add a few flying capacitors, you can use these capacitors to effectively decrease the voltage seen across the inductor as it's switching, and therefore effectively decrease the inductor size through either switching at a higher frequency or other approaches. Okay, So this is the promise of hybrid converters. Now, there's all sorts of challenges associated with them. If you implement this directly in 28 nanometer, you'll find that this flying capacitor here has to block 2.8 volts. In that particular process, we don't have a 2.8 volt capable capacitor, which means we need to stack capacitors, and it basically takes 4x more area for that same capacitor. And so we can modify the topology by adding a couple of extra switches. This drops the capacitor rating to 1/3 VN instead of 2/3 VN. Yes, we now have extra switches in our stack, but it turns out the overall trade-off is a favorable one. And my slides are freezing again. Okay, so I'm running out of time a little bit here, so let me just effectively jump to the punchline. So this is the measured results. Again, this is in a 28 nanometer FD-SOI process. And in this particular case, we actually put the inductor right on the chip here. Now, this is not advisable if you want the best possible efficiency, but we wanted to try it to see how well we could do with a totally fully integrated converter in 28 nanometer operating from lithium-ion batteries. To our knowledge, there's no other converter published today that does this. And so the efficiency we can achieve is actually pretty good, given the constraints that we had. The peak efficiency was about 79%, which given a poor quality on-chip inductor was pretty good actually. We were pretty happy with this. Because we were operating in discontinuous conduction mode with some of the same techniques that we showed before, we could get high efficiency across a wide dynamic range of power, and improving the efficiency of a comparable, say, integrated LDO by about 40 or 50%. Okay, so I'd like to conclude my talk. IoT devices don't require much. They only require multiple power rails. We need to regulate over many different supply voltages over wide dynamic power ranges, all from high voltage lithium-ion batteries, possibly with energy harvesting capabilities in small form factors with high efficiency. Okay, not too much to ask. Okay, it turns out that achieving everything there is hard, especially if you want to do it in scaled CMOS. So we need to be careful about how we do this. We need to be careful about what kind of topologies we select. We need to be careful about how we use our process capabilities. We have to be careful about how we use our resources in terms of our switch sizes, our inductive resources, our capacitive resources, and so on. But the bottom line is that there's still many challenges moving forward, and this is a really fun space to be designing in. And so with that, I'd like to acknowledge some of the work by my students, particularly Sally and Lawai, who did a lot of this initial work, ST Micro for supplying the chips, and the rest of the students in my group. So thank you very much.
Thank you very much for the wonderful presentation. The talk is now open for questions.
On your multi-modal circuit, you showed that switch with two fans in series. I don't understand the 0.9 volts in junction of those two devices. Are they identical?
Yes. That's right. So they're 1.8 volt capable devices in that particular implementation. And so when you turn them both off, okay, point taken. It's not going to be exactly 0.9 volts because one device is in super cutoff and one is not. So that was just more for illustration to say that the source of that second switch was going to be much lower than the gate voltage, which puts it into super cutoff. The exact voltage you'd have to go ahead and simulate because it's a little bit more complicated than that, but it's definitely going to be less than 1.8 volts.
I guess I still don't see how it's any better than just a FET for longer time.
So you're exploiting the super cutoff regime, right? So when you go into subthreshold, you have this exponential slope. When you have negative VGS, absolute value, if you will, for PMOS, that exponential slope continues to go down. So you get exponential current decrease rather than a linear one with an increase L. And you don't want to increase L because you also want this transistor to have a low R on when it's on. So you really don't want a large L either, right? So going into super cutoff is a way to effectively increase the R off without adversely increasing the R on. Now, of course, because you're stacking two switches, you have to double the size of the two switches to compensate, but that's a worthwhile trade-off.
I had a question about the freewheeling mode in the when no nodes and no sources are connected. And my question was, in that freewheeling mode, because you're going through switches, do you lose some of the energy stored in the inductor?
Yes.
Is that any important?
So the short story is not really. So the reason we like the freewheeling mode is if you don't have the freewheeling mode, then what can happen is if you turn off the switches a little too early or a little too late, and you still have current flowing through the inductor, you're going to get ringing, right? That ringing, that's going to dissipate somewhere. It's going to go through the parasitic diodes or something like this. That ringing can potentially have large voltages, which has some reliability issues. So by turning on the freewheeling phase, you just kind of cut those out. Now, yes, if there is any residual current in that inductor, you're shunting it to ground. But in the alternative scenario, you're not doing anything very efficient with it anyways. And so for reliability reasons, it's better to just squash it all to ground. It turns out that if you're doing ZCD well, then that amount of residual current and therefore energy is very low. And so this doesn't really adversely affect your efficiency.
The limiting of the switch size is a factor not depending on the big current we have in the
Correct, yes.
So what's going to be how do you manage the switch sizes?
Yeah. So it depends, right? So what do you want to optimize for? Do you want to have the best possible efficiency at peak? Do you want the best possible efficiency at somewhere at back off? How do you select your largest possible size switch? How do you sense what conditions you're in? How do you determine what nodes are going to need this and so on? So there's separate calibration loops for the battery, which has to support the demands of all loads. And so if one load needs a lot of power, then the battery switches are going to be the biggest possible, right? Even if the other loads don't need it. Now you could be clever and try and do this dynamically and say, okay, I know I'm delivering power only to one of the low power loads, so let me not use the big battery switches. Let me use the small ones, right? So you can have intelligence in your controller to do that. Now, if you know that you're going to deliver power to load 1, which is a high-powered load, and then you subsequently have to deliver power to load 2, which is a low-power guy, then you have to make the choice as the designer, do I want to use the large switches to make sure that the efficiency of the big load is maximized, or do I not care about that and care more about the low-power load? In this design, we said the high-power load is more important, because obviously you'll lose more energy across it if you don't have the larger switches selected. So there's a lot of details in the controller that I didn't have time to discuss. These are some of the things that you have to think through before you tape out. Yeah.
All right, any further questions? Okay, so let's thank our speaker one more time, please.